Hello and welcome to an extra special spooky math video. Today we are talking about the Moivre theorem. All right, so what is de Moivre's theorem? Well, it states that for any complex number and any n in the positive integers, you can write z to the n as r to the n times cosine of theta n plus I sine theta n. Now, the question arises, as it always does, what does this mean? Well, I'm glad you asked. We are going to get into it, but first we have to talk about complex numbers and the complex plane. So, complex numbers are numbers usually in rectangular form down here. So it's going to be all complex numbers can be written in the form x plus iy. And we can talk about the complex plane, which is going to use the real number line as the x-axis and the complex numbers as and a complex y-axis. So that y-axis is going to be all the values, which you can see sort of down here, which have I in them. And for any of you unfamiliar with I is going to be the square root of -1. All right, so what does that look like? So I've got my z up here, and we just sort of learned that this z can be written in terms of x, I, y. And let's just sort of pop some values in here for x and y. I'm going to choose, not so arbitrarily, but I'm going to choose √3/2, and I'm going to choose 1/2. So we get for our z is going to be 1/2 plus I. Remember, this is the imaginary line up here, and here's our real line. It's going to be 1/2 plus I times √3/2. All right, sounds pretty good. But where did all these thetas and cosines and whatnot come from? So some of you may be sort of familiar with polar form. Now, what is polar form? Well, we can do polar form in R2 as well. And just like R2, polar coordinates our complex numbers can be written using x equals r cosine theta and y equals r sine theta. So sort of to demonstrate what we're going to do here is imagine a line that's going from the origin of our complex plane, and it's going straight to that z. So this does a few things for us. First off, it creates this angle theta right here. And secondly, it creates what some of you may recognize as a right triangle. And right triangles have all lovely properties. But before we get into that, I'm going to name this line R. And what do we know about R? Well, we know that this bottom length down here is going to be 1/2. And we know that this sort of top length over here is going to be √3/2. And if we do our old Pythagorean theorem, we get that 1 squared plus √3/2 squared, which gives us 1/4 and 3/4 equals 1. And so now we know that our r over here is going to be 1. Oops. 1. All right. So now let's just go ahead and solve for theta here. So we know that the sine of an angle, if you remember SOHCAHTOA, the sine is going to be the opposite over the adjacent. So that's going to be this side divided by this side. Luckily, that side is 1. So it's going to be sine of theta equals, what is this? √3/2 divided by 1, which is just √3/2. If you remember your trigonometry, there is a nice easy angle in radians that you can plug in for theta that will get you √3/2. That turns out to be sort of, if you imagine like a nice little circle that goes all the way around this plane, right? I have to travel up pi thirds radians to get there. So sine of theta, that becomes sine of pi thirds equals √3 over 2. Lovely. And theta remains consistent, so we get cosine of theta. Cosine of pi over 3 is 1/2. And that checks out because we had 1/2 down here in the x-axis, or the real axis, and then √3 over 2 in the imaginary axis. And we just stick that I on because it sort of helps us separate the different axes. So since a complex number is written as z equals x plus iy, we can actually rewrite all of these complex numbers to be z equals r cosine theta plus I r sine theta. So that sort of gets us one step closer to understanding Dumois' theorem. So what's next? Well, Dumois didn't actually prove his theorem. He sort of just stated it, and it took a little while until Euler actually was able to prove Dumois' theorem for all positive integers. So the main idea that Euler had was that he can create a Taylor series, and we can create a Taylor series to show us that cosine of theta plus I sine theta equals e to the I theta. And as an added bonus, we can also use this to show Euler's identity, which is e to the I pi plus 1. So let's just write what we want to show here, which is going to be the Taylor series of cosine of theta plus I times the Taylor series of sine theta. We want to show that that's equal to the Taylor series of e to the I, should not be x, it's going to be e to the I theta here. All right, so Taylor series of cosine, I just wrote out a couple terms here, 4 terms. So we get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. If you'll remember, both the sine and the cosine Taylor series expansions alternate. So they sort of have that -1 to the k in them, or -1 to the 2k plus 1. So they, because they alternate, it's actually going to help us solve this sort of above equation here. Similarly with I sine theta, the Taylor series expansion of sine theta, and then we just multiply the whole thing by I. And so we get ix minus I x cubed over 3 factorial, and so on. So here I just wrote out the sigma notation of e to the ix, and that is going to be from starting at k equals 0, we get I times x to the k over k factorial. And so let's just start. I wrote out 3 of the terms here, but I want to write out a couple more so we can see something interesting that happens as we sort of continue down this line. So we start at 0, then we start at k is 1, then we have k is 2, and now it's going to be k is 3, so it's going to be I cubed times x cubed over 3 factorial. And we'll do a couple more. I to the 4th times x to the 4th over 4 factorial, and let's just throw one more in, because why not? I to the 5th times x to the 5th over 5 factorial. Now, we have i's here, and we have powers, and something about I that we know is that I is equal to the square root of -1. So I squared equals -1. And I see a couple I squareds here, primarily in this term here. So we can sort of bring this down, and we know that that's the same as -1 times x squared over 2 factorial. And we know that this is going to be I squared times I. I squared is -1, so it's going to be -1 times I times x cubed over 3 factorial. Similarly to this is I squared times I squared, or -1 times -1. That gets us +1 times x to the 4th over 4 factorial. And then this one is going to be, let's just write it out in case it's sort of difficult to understand what I'm talking about here. We have group all these I squareds up, so that's -1, -1, and then we pop an I on. So we get that it's -1 times -1, which is +1 times I times x to the 5th. So it's going to be I x to the 5th over 5 factorial. And we can sort of keep doing this for e to the ix. And what ends up happening is that we get these terms here and here and here. And all of the odd power terms, right, that's x to the 1, 3, 5, end up having the I in them. And all of the even powered terms, which is going to be 1, I guess 1's not really even, but it's a little special case. We have x squared, x to the 4th, and x to the 6th. Because they're even terms, their i's cancel out, right? It sort of makes sense. If I is made up of, right, if 2 i's equals -1, then sort of any even power I, like I to some 2n, is always going to be some either negative or +1. So we look at these powers, and I sort of scroll back up here. What we have is that the odd powers end up being reflected right here, and they alternate in the same way that cosine theta does. So when we had the second term in the Taylor's expansion of cosine theta, that was -x² over 2 factorial. And what we had here was we did I times I, which was -1, and then times x², and then we sort of brought this down. That's not a great line. We brought this down here, and it ended up being that this was a negative term. And similarly for x to the 4th, we have a positive x to the 4th up here, and down our e to the ix, we also have a positive 4th because that was -1 times -1. And for our sine of theta, you'll notice that we have ix, negative I to the x cubed, negative I to the x cubed, and we have positive I to the x times x to the 5th. And if you want to keep going, we can even write minus ix to the 7th over 7 factorial. All right, so what we've just shown here is quite interesting, and that's that cosine of theta plus I sine of theta equals e to the I theta. And this is really critical for understanding de Moivre's theorem. All right, so turns out this is equal to the Taylor series of e to the ix. Let's go back to de Moivre's theorem. We want to show that r times cosine theta plus I sine theta, which, if you'll remember, this is a complex number. In fact, it's not just a complex number, it's any complex number. Yeah, and we take that to the n, is going to be equal to r to the n times cosine n theta plus I sine n theta. So since we now have found that any complex number can be written in polar form, and any polar form of a complex number, we just found that this little bit here was equal to e to the I theta. And so if we just multiply that by r, we just get r e to the I theta. And that's also any complex number. So we just do a little bit of an exponent rule here, and we get that r times I to e to the I theta to the nth power is going to be equal to r times r to the n times e. And if you remember sort of power algebra, the taking something to the power to an additional power is the same as multiplying. So we get that power just stuck in there. And what we found out was that if we back substitute here, we get Rn times cosine theta n plus I sine theta n. And there we go. So we can conclude, therefore, for z in the complex numbers and n in the positive integers, z to the n equals r to the n cosine theta n plus I sine theta n. All right. And just like that, we are done. That is Dumas' theorem. But as a bonus, I would like to sort of walk us through why Euler's identity sort of works out to what it is. So Euler's ID is e to the I pi equals, e to the I pi plus 1 equals 0. All right, so what does this tell us? Well, if we think back to our complex plane here, right? And remember, I had this point, it was about here, and it was root 3 over 2 and 1/2. And I chose these numbers very specifically because these are numbers that sort of show up in the unit circle, so it becomes fairly easy to find out that this is pi over 3. But what if we just had pi instead, right? So I know that pi over 2 is sort of this angle right here, and I know that pi ends up being this whole angle theta right here. So let's just pop this right here, and let's say this is 1 because our r is sort of staying consistent here, and I'm just moving this line all the way down here. Well, let's put this in polar coordinate form. So I have some r, which is r equals 1, so it's going to be 1 times cosine of pi plus I sine pi. All right. And then we also want to add 1 to this, and this should give us 0. So let's evaluate. Well, sine of pi gets us 0, and so I times 0 is 0 plus, and we have cosine of pi, which ends up being -1. And just like that, we get that -1 plus 1 gets us 0. So e to the I pi plus 1 equals 0. All right, I hope you guys enjoyed, and I will see you in the next video. Peace out.